Thanks for very correctly pronouncing the name. Like, yeah, not sarcastic or this is a really good pronunciation. And today I'm sharing this idea. Me and my PhD supervisor Jeremy are kind of doing with a combining dependent types and assembly language. And you might start thinking, okay, why is this possible, and why would anyone really care about this? And but I can tell you at least about the motivation a little bit because there is a very, I don't know, unfortunate fact that we are immediately throwing away all the dependent types after we type check in all of the existing compilers, which is not a bad thing because they have fulfilled their mission to, verify that our source programs are correct. But I think we know that there are some very good reasons to carry the types through intermediate stages of compilers, and from these very relatively old work of type intermediate languages that we carry the types into some fully typed program transformations, and they can, guide the transformation like CPS, like defunctionalization, codec conversion. We know that for system F-ish type systems, they are well typed, and you can also to just get more information with optimizing. And if you take this to the furthest level, you can basically preserve your source language type all the way through the compilation pipeline, and you produce a fully typed assembly language as the target, which is the output of your compiler. And there's a whole line of work called type assembly language on this. But what I'm trying to say is you can get a so the very good reason of preserving these types is that you get some kind of confidence. You can type check your code, and you don't have to rely on compiler correctness to do this. And if we can preserve the dependent types to the lowest level, then we have the highest level of confidence, which means that your compiled code behaves correctly, has all the correctness properties that you've shown with fighting a glorious battle with the type checker. And to your surprise, this is a much older problem than you expected about combining dependent types with assembly. I think the oldest one I can find dates from 1993, but it's never been a very satisfying solution. But I think maybe now is the time. So let's look back again on this problem of dependent assembly. What are you talking about? I mean, I guess types depend on terms, which are now computations, which are now assembly languages, as instruction sequences maybe. And what about then what does it mean? Do I need equational theory for like instructions? What is a dependent stack? And all of that, it seems like a bunch of nonsense. And I would say that, right, it is a bunch of nonsense. The real design I want to present is that we should separate high-level dependent types and the low-level assembly code like completely. And so the syntax is going to be a two-level syntax like this, with one assembly language right here. It's describing, it's an instruction set for stack machine, and it's describing the lower level computation with the usual thing you might want to see, like pushing a literal, popping something out, fetching a variable from a runtime environment, forming closure applications and sequences, etc. And there is a term calculus which describes from a higher level, what is the expected computation of the assembly code, which is a fully dependently typed calculus with a syntax like this. But so let me start with the term calculus. It is not just an arbitrary like dependent type calculus, but it's a specialized form called defunctionalized calculus of constructions, which is exactly the same, or basically the same as the original CC, except that because we need to cope with lower level, form, there is no lambda abstraction you can use. Very sad, but there is a fixed set of what are called function labels or code labels in the context, and you can only form a function by pairing this label with a list of terms to form a closure. So here I have a list of terms, and in gamma they have a types context delta. And in the also in context, I say that this label is specified with, this closure that the delta is three variables. X of type A is this input, E is the function body, and B is the type. And you can form the label with this list of terms to get a pi type. Well, of course, you need to do with substitution. So this is based on our previous work. And we have ways to just generate these labels from a given source program in CC, and we show that this calculus itself is consistent, and the defunctionalization transformation is type preserving. And well, with the term calculus done, we and the assembly language is as traditional as it could be. It's a stacked machine where, oh, sorry, what have I done? Okay, so the runtime values here, so it operates on, stacks and a bunch of runtime value, which are closed values in term calculus. So either some base values or closed types or closures, which is a label with a bunch of values. That's all the data I'm operating on. There's no crazy dependency here. Everything is very basic. And a machine state is, of course, a control, environment, stack, and what they used to call this dump. I think the more like a modern name is a stack of function call frames, where this I is a set of instructions. Environment and stack are runtime environment and temperate computations, the list of runtime values, and this frame is basically a stack where you store the core frames. And I also have a mapping list of procedures that maps function labels to instructions, and a machine step has this is written in this form. Okay. So I just realized I don't have an example program. That might be a bit sad, but we could at least just imagine something. There's some example program in abstract, so check the abstract if you really like one. But anyways, now with the term calculus and assembly language done, we can actually try to type an assembly code with the term calculus, which its judgment looks like this. So it says that, first of all, an abstract stack sigma is nothing but a list of terms in the term calculus. And typing judgment is pretty much the same as the usual stack typing, but except that it says that this instruction I transforms a stack of content sigma to a stack of content sigma prime. And in principle, it should be kind of modeling the computation of the instruction is like an abstract interpretation scheme. And what I mean is exactly is like this. So at the left-hand side, you have the typing rules. So for the simple ones, for example, var x, which is fetching x from runtime environment. What we get to the type is, okay, this instruction transists the stack sigma, contains sigma, to a stack containing sigma followed by x. And operationally, it really reflects this by if my instruction is var x and then something else, then it transists to I remove the top instruction, I fetch a value from the environment, which according to x, and then I move on. And the similar thing goes to pop. Okay, I am using some different symbols here, but so the type of pop is if you have some term on top of the stack, then it's gone. And as shown here, it's like this. And so this is really very conventional, and the same-ish thing goes also for closures and applications. So for the closure rule, this is very much like the closure rule for the term calculus, where you have a list of terms of satisfying the type of three variables to be supplied with a closure. Then this instruction clo n lab will just make a closure with the top n items on the stack and pair up with label lab. And this is exactly what it reflects operationally. If I have this closure instruction on top and I have n items on top of the stack, then I will make a closure item from taking the top n items right here. And application, the typing is really simple, because as long as I have two things, one is the function type, one is the argument, I get the result here. but operationally you will have to well, first of all, make sure that you can only step if this second top value is a closure, and then you step by looking up what code correspond to this label and load it to here, and then you filling the environment by using the closure environment and the input. You clear the stack, and of course you store the current unfinished computation on top of the the stack of frames. And so that basically concludes the setup of the language. That's the syntax and typing and operational semantics. And I think and there are the two ways we can proceed with this. One is the usual type assembly language way that we move on to define a compilation function to generate assembly code from a given program in the function like CC, which is very straightforward, and you basically just copy whatever that's up here structurally. There's really nothing interesting going on, and we're able to show this is like immediately type preserving in the sense that whenever you have a well-typed term, you can compile it to a instruction that generates this well-typed term on top of stack, and eventually you with some fighting, you will be able to show that this is correct in the sense that if you have a well-typed program and it terminates and to some value, then the compiled thing also ends with the same value on the top. But I think we can do something a bit more with such setup, because if you look closely or remember what I said earlier, that we know runtime values are nothing but just close the values in the term calculus, which means that they can be typed very easily just with the type system. And since the environments and stacks are just list of runtime values, there's no reason they cannot be typed. We can also type them with certain judgments, maybe saying that environment implements a context of type gamma, and a stack implements an abstract stack sigma with respect to some environment. And we have the same-ish judgments omitted, but I can I'll have the judgments for the frames and procedures, and all of these constraints will combine into a well-formed judgment for the machine states, and which means that we can now type machine states. And with that, we can really just treat the assembly language as a program language of its own, and look at its metatheoretic properties like type safety with progress and preservation. By the way, these are true. They're not just here. I've proved this. So as you would expect, so well-formed things moves to well-formed things, and the types are preserved. So what I want to say is this opens much more opportunity for a lot of future work. For example, you might want to investigate the termination of the target language. And one reason is that termination implies the correctness of compilation. And second is you might want to do some certified optimization with this. It's possible to take the assembly out and do whatever crazy thing you want to do with it, and then stitch this back with the type system and see if this is still well typed. And if it is still well typed, then you have complete faith with your optimization scheme, even though you might throw some dark magic in there. And of course, there's many things I can work on. For example, in the abstract, there's a link in the aggregate formalization meta theory. For your assembly language to be really useful, you need to care about the erasure of runtime types, and one should also add data types, runtime notations, and possibly quantitative types for better erasures, and maybe also linearity in future. I think I should stop here. Okay.